In terms of land use, as I showed you before, we have these 2 units of EC6, or in fact it's Candu 6, the enhanced Candu is the evolution, but 2 units of Candu 6 at 1360 megawatts here, shown in China. That is the currently largest solar power station in the world in the United States, known as SEGS, rated for 350 megawatts. So you can see we're getting 1360 megawatts on essentially a spit of land in China, and you can see the landscape scale of attempting to make baseload power using the sun. There is plenty of sunlight, but it's very dilute or dispersed, and the challenge is actually capturing enough of it and storing it and concentrating it, and that takes up a lot of space. The exact numbers provided are that the renewable solar option would require 16 square kilometres of exclusive land. So if you've run the city to bay, then you've run 3/4 of the perimeter, would be one way of thinking about it. The renewable technology, you can think in terms of the exclusive and non-exclusive use. In terms of exclusive use being the footprint of the actual turbines, the service roads and the buildings, it's about 2.1 square kilometres. In terms of the entire project area that encloses all of the individual turbines, it's a very large area, about 175 square kilometres. The nuclear, we have selected 2 square kilometres based on taking the area of that plant shown and about 70% of that area, because we only need 1 of the units. So quite a big difference there in that criteria. Water consumption is something that people are often curiously sceptical of, I guess, in terms of nuclear power. A wind turbine essentially is a zero water energy producer. The blade is being spun and energy is being generated from the turbine. The solar thermal and power towers will require clean water for washing the mirrors every year, but they have stated in the reference case that they would be air cooled. The present setup in Port Augusta is ocean water cooling for the thermal power stations, and that is exactly what is happening here. So there is essentially, under the nuclear reference scenario, no change in the current water arrangement, which isn't drawing on any freshwater supplies. So I guess we need to distinguish between water consumption and perhaps potable or potentially potable water consumption is more the point. So the renewable solution does require 0.74 gigalitres of fresh water annually. The other 2 types of energy generation are not competing with potable water. Material inputs. Again, we use this criteria mainly in order to perhaps address a common criticism of nuclear power, not necessarily because we feel that this criteria should make or break the energy decision, but we do think there's some interesting information here. But again, the quality of the information was a little varied. In terms of the concentrating solar thermal, the reference report for the renewable solution gave us information for the heliostats only and not the towers. So I guess fair confidence there, but it's certain to be an underestimate. In terms of wind, there is good general literature. However, we didn't have anything specific to the Enercon turbines, so I guess we'd call that good. With the nuclear option, we had very detailed and extensive estimates for the Candu 6 from that construction project in China. So we have excellent confidence there, and you can see that in the graph with the quarter by quarter consumption, in this case of concrete, and the red line going up is the overall consumption to the end, and the box in the middle gives us quite good details about just what they had included in that estimate. So it was very good to have such good data there. To really understand it though, we actually need to combine a few criteria. So in terms of the material inputs, just at the baseline, the nuclear does come out with something of an advantage here. Slightly more concrete than the overall renewable solution, but far less steel and essentially no glass of the 3 materials that we considered. But if we go back to both the lifespan and the annual output, we know that we're getting longer life and higher output out of the nuclear plant, in both cases by quite a lot. So the bottom line is that under those assumptions, we actually end up with 3 times the lifetime output, or nearly 3 times, of zero carbon electricity for that input of materials. So to consider that criteria in a way that is appropriately context we need to take that into account. Capacity factors, this is our next bit of jargon, but again, important jargon. The capacity factor is a ratio. It's a ratio of what a generator could produce according to its rating if it were running non-stop all year versus what it does produce. So in a nutshell, it's one divided by the other. Example there of a wind turbine, if it was capable of producing 65,700 but it instead did produce 21,900, the capacity factor given would be 33%. That's about typical of a wind turbine. Now that speaks to the overall variability in the intermittency. It doesn't mean that it only runs 33% of the time. That's not the way capacity factor should be interpreted. Again, fortunately we had very clear information here. 30% assumed for the renewable, 40% for the solar thermal. The nuclear EC6 is rated to about 90%, but for our analysis we assumed 85%, which is basically starting to give you the clue that the nuclear is a highly reliable way of delivering electricity. Which brings us again to reliability, which is in words probably the longest section of the report in terms of the criteria analysis. So we've gone into quite a bit of detail in the report. I'm going to try to sum it up in the simplest possible way I can here with a slide, which is this. Solar plus wind doesn't equal coal. So it is not the case that you can simply merge or hybridise two intermittent, climate-dependent generating solutions and provide the same service as a coal-fired power station. You may provide the same quantity of electricity. There is no assurance of providing the same service. Nuclear, for all intents and purposes, equals coal minus greenhouse gas. Here we are providing both the quantity of electricity and the service in terms of fully dispatchable, always available electricity that is highly reliable. Bottom line being that under the renewable reference scenario, South Australia's electricity supply would have diminished reliability, and under the nuclear scenario, it would be undiminished reliability. In terms of job creation, again, for us, this is not a make or break criteria for how the decision ought to be made, and it would appear from the information that was available that both options provide a good job creation outcome. That should be expected when such sums of money are being spent. That's not any particular surprise, but certainly the nuclear does provide a very healthy job creation outcome, and certainly the ongoing jobs are some pretty enticing ones. Network enhancement refers to any challenges of actually getting these solutions connected. And there's a little bit of interesting story to tell here. In terms of the renewable solution at the local level, i.e. where we would want to plug it in, there is no specific barrier identified. In that region, the infrastructure that is there would probably cope with what's being provided to it. We undertook some consultation with Electronet, and they were able to confirm that. On the broader picture though, the sheer size of this in terms of new intermittent capacity being added to South Australia would suggest that we would need to be moving towards this green grid situation of network interconnection with the other states in order to actually share this electricity in an economically efficient way. Already with the high penetration that we have of wind in South Australia, there are negative price events occurring. That's another way of saying overnight so much electricity is being produced from the wind that it's exceeding demand. The price of electricity drops below zero and electricity is essentially being dumped. That's a consequence of progressing to higher and higher levels of penetration of a generation source that is intermittent in the way that wind is. So you can see in that image on the right, that's taken from Worley Parsons' Green Grid report for the South Australian Government, identifying potential interconnection. So with such a large addition of intermittent capacity, I think it's very probable that it would need to accompany that. The nuclear solution has a different problem, and that's the size of the single generating unit. So bear with me here, but at the moment, the South Australian grid is permitted to lose up to 260 megawatts of generation at a time. In a single contingency event, that's how much it can lose. That's how much it's regulated to lose. It's modelled at the moment to be able to lose up to about 650. It's not modelled to lose beyond that. Which is another way of saying that because the EC6 is 680, it's too big to plug in at the moment. the coal that it's replacing, Northern and Playford, is actually split up into 3 separate generating units, the largest being 260. So that's that regulated limit. So there are ways around that, which is either the enhanced interconnection, new large sources of demand in South Australia, or perhaps investigating what I've shown here in an image, which is small modular reactor technology. So where the single generating unit is at 180 megawatts. That would be no problem, and you could run a few of them in a series to get that outcome. So there would be potentially ways around that. Interesting message though, I guess, out of that is that an enhanced network is good for all comers. Everyone benefits from a better, more interconnected network. Finally, the existing global and local capacity. We wanted to get a feeling for how challenging it might be overall to get these technologies going on the basis of how commercially mature they are. So if we were to deploy the nuclear solution in Australia, this would be nationally significant because we have not done nuclear power yet in Australia. Globally, however, that would be entirely manageable. It wouldn't be far off trend currently with growth of nuclear, and technologically it would be completely unremarkable. This is very mature technology. For solar, this isn't the case. If this reference solution went ahead, we would be creating by far the largest single facility in the world for solar. It would be 76 times bigger than currently the largest Australian solar. And so I guess we have added a note of caution that perhaps the solar industry should be consulted a little more carefully about whether this is actually the best stepping up of solar for Australia. And some friends I have in the industry have suggested they might be a lot more interested in perhaps a few medium-sized projects before going after something quite this big. In terms of wind, it would be a 58% increase in the wind capacity of South Australia, and that would be difficult. Again, just to put that in some context, there's the world's largest solar, that's 350 megawatts. There are 65 gigawatts of nuclear under construction in the world at the moment, and 175 gigawatts of it either on order or planned. Not proposed, on order or planned. Proposed is quite a bit more. To conclude, we do have options. There is not only one way to decarbonise. And this option could mean 10% more greenhouse gas abatement per year for about half the capital cost, providing a significantly cheaper source of electricity that is completely reliable, consuming far less land and no fresh water, requiring less material resources to build with over double the lifespan, that uses our local fuel source and provides high-tech jobs deploying a commercially mature technology. So it would appear to me that there's really only one question left to ask, and that is this: is Australia ready to put this option on the table? And ultimately, that's what the nuclear advocates that I spend time speaking to are seeking. To please have the option put on the table, at which point we're very happy to see the processes play out. We're very happy to see this technology compete.